Today we're going to talk about inductance of a single phase circuit, and this is going to be part one of our discussion. We're going to derive the equations for the flux linkages today, because that in itself is going to take a little bit of time, and I want you to clearly understand that before we move on to in the next video deriving finally our equation for the inductance of a single phase circuit. Before we start though, as always, let's do a quick recap. In the last video, we saw the inductance of a conductor of a number of conductors till a distance p, and we got a general formulation for any conductor in that group of conductors k. If you haven't already, please see that video because I am not going to be spending any time recapping that. We have a lot to cover in this video itself. So just the formulation here because we're going to be referring to that. What we concluded or what we derived from our last video was that lambda kp, where it's the flux linkage for any conductor k in a group of conductors up to a point p, and we'd considered p to be infinitely far away. So this basically gave us the formulation for all the flux linkages for conductor k. So that was given by 2 into 10 to the power minus 7 sigma j is equal to 1 to n, where n is the total number of conductors, I of j ln 1 of dkj. And then we said for the case where j is equal to k, dkj was nothing but r prime k, where r prime being 0.7788 r of k being the radius of conductor k, and this was Weber turns per meter. Once again, if you haven't seen the last video, you will not understand this, so I really encourage you to please go and see that last video. I just wanted this formulation to be here because we will be using it. Some other things we'll be using, I know we've used this in the past, but I wanted to kind of just spell this out once again. Some properties of ln of a plus b is can be written as ln ab. Ln of a minus b can be written as ln of a over b. These two we've seen and used in earlier videos. One new one property that we'll be using today is a ln b can also be written as ln b to the power of a. So before we dive in though, there's one other concept that I want to quickly touch base on, and that's of composite conductors. So let me just write that down here. Composite conductors. So far what we've seen is only solid cylindrical conductors, but composite conductors is a special case where you have two or more conductors, or rather strands as they call them, and they are electrically parallel. So they basically form electrically a parallel circuit. So as I was mentioning, so far all we've dealt with is a solid cylindrical conductor. But we're going to take up a general case where, inside your conductor, inside your solid cylindrical conductor, and which is more of a real life scenario as well, um, you'd have strands. So you'd have strands that are electrically in parallel, right? So there could be, so this conductor is actually not a solid conductor by itself, but it's composed of many strands in there, right? So we're going to consider a single phase circuit. So we're going to consider for our a single phase composite circuit, and the reason we're doing that is because this is a general case. The equation we get for this is going to be a generic equation that we can use for various different applications. And what I'm going to do is, once we derive this, I'm going to have another video where I solve this example, solve the case of a solid conductor. You're going to use the same formulation that we derive using our formulation in this video and the next, and the inductance formulation that I get, I will use that same formulation to show you what the inductance would be for a single phase conductor having just a solid conductor. So we'll do this generic equation. So the only condition we have here though, one, that these strands be cylindrical. So we have cylindrical strands. And the other condition would be that all these strands share the current equally. So they share current equally. Let me just draw a quick cross section of this for you to clearly understand. So we would have conductor 1, this is sorry, strand 1, 2, 3, so on up to n strands. And this is going to be conductor X. So this is conductor X. And then we have the return conductor. So remember, this is single phase circuit, right? So you have a conductor that is bringing power to your load, and then you have a return conductor. So current flowing this way and current flowing back, right? So that's your single phase circuit, for example. So that's conductor X, and then we have the return conductor, conductor Y. And let's say that has strands 1 prime, 2 prime, 3 prime, so on up to M. So that has M strands. Now notice how the number of strands do not need to necessarily be equal, nor the properties of these strands need to be the same. The only thing is, in this conductor, all the N strands share the current equally, and in this all the M strands share the current equally. So let's say the current in this is going in one direction, the current in this would be coming out in another direction. So this is conductor X, this is conductor Y. The current in this is, so this has N strands and this has M strands. The total current in this is I. Total current is I. The total current here would be minus I. So the current per strand in this would be I over N, and the current per strand in this conductor would be minus I over M. Right? So that should be pretty clear from this diagram and the discussion we've just had. So we're going to take a single phase circuit that has composite conductors, right? With N strands and M strands. Now let's get into the formulation. So we're going to use this formula right here. So let's start doing our derivation. So let's consider, let's start with conductor or rather strand 1. So in essence, again, this strand is cylindrical. So we can basically use the same formula for the conductor. It is a very small conductor, a conductor of very small radius. So if we do lambda 1, again to the point P, but P is infinitely far away, so all the flux linkages for conductor 1 can be given by that formula. So we're going to say that's going to be equal to 2 into 10 to the power minus 7. And then we have I1 ln of 1 over d11. So d11 is that special case which is dkj, j is equal to k. So in essence, d11, let me just change the color here and just say d11 is nothing but r1 prime, right? It's 0.7788 times the radius of that strand, r1. So now continuing with our formula here, so that's going to be I1 plus I2 ln of the distance between strands 1 and 2, so on all the way to IN ln of 1 to n. Now you don't finish here. Remember this, though this is within conductor X, conductor Y is close enough to influence the flux, to have flux linkages with conductor 1, right? This is not the case where in our initial videos where we considered an isolated conductor. Here you have another conductor in proximity. So all these strands that are in conductor Y, the current through these are also going to be linked to the going to have the flux linkages with conductor 1. So, but what I'm going to do is I'm going to and the formulation is going to be the same. It's just going to be a continuation. Let me just change the color though. So what that's going to be is it's going to be I1 prime. That's the current through the strand 1 prime, ln of 1 over d1 to 1 prime. This is separate from this. This is the distance that's from strand 1 to 1 prime. Similarly, I2 prime ln of 1 over d1 to 2 prime, so on all the way up to this strand M. So I of M 1 over d1 M, right? So then you have two parts to this. There's this part in the blue here, the second part, and this first part in yellow here. So all of these strands, the current through all of them has an influence on the flux linkages in strand 1. And so they're all captured here, but we've just separated these out, and you'll see why, because that's where our math will get interesting. Now, we know that the current shared equally. So what? So that's just step 1. So step 2, we know I1 is equal to I2 is equal to so on is till I of n, and they're all equal to I over n. That's what we wrote here. Current per strand is equal to I over n. Similarly, I1 prime is equal to I2 prime, so on all the way up to I of m, which is equal to negative I over m. So now we're going to substitute all of these values here. So what do we get? We get lambda 1 is equal to 2 into 10 to the power minus 7. And we're going to, so I1 can be written as I of n, I2 can be written as I of n, so on. So we're going to bring I of n out, makes I of n ln 1 over d11 plus ln 1 over d12, so on all the way up to ln 1 over d1n, right? And then let me change colors for the second term now. So this is going to be minus I of m, right? We're going to substitute I1 prime, I2 prime, everything by minus I of m, and then we're going to get ln of 1 of d1 prime plus ln of 1 over d12 prime, so on all the way up to ln of 1 over d1m. Okay, so that's, we just manipulate these terms here to get this equation. Now let's go to our next step. Here we get 2 into 10 to the power minus 7, and we're going to all of these ln terms, so that's ln a plus ln b, all of them can be written together, and we're going to take I out of the brackets as well, so you can get 2 into 10 to the power minus 7 and you have I outside. So inside now you're left with 1 over m ln of 1 over d11 times d12, so on all the way over to d1n. Okay, and this is going to be just change colors, minus 1 over m, the same thing here, 1 over d1 prime, d12 prime, so on all the way over to d1m. And let's close the brackets here and here. So you have this multiplied by this term, and you have minus 1 by m multiplied by this term here. Why this is, let me remind you just again, I'll put that in the brackets here, and this is, let me write it another color. This is because ln of a plus ln of b is equal to ln ab. So basically ln of 1 over a plus ln of 1 over b would be ln of 1 over ab. That's just that property we're using here to combine all this, and we've taken I out in the common. That's all we've done in this step. Next step, you remember how I mentioned up here we're going to use another new property of ln, which is a ln b is equal to ln of b over a, b to the power of a. Well, does this look similar to that? A ln b, so we're going to make that ln of a to the power b. So in this step, all we're going to say is, so just to make it easier and so that I don't have to write this term again and again, or should I continue writing it? Okay, let me write this term once again and see if it gets a little too confusing. I'll probably um, give it another abbreviation or something. So let's see this. I, and then you have ln of 1 over all of these terms, d11, d12, so on all the way over to d1n, and this to the power 1 by n, and now your second term is going to be similarly minus ln of 1 over d1 prime, d12 prime, so on all the way up to d1m, and all of this to the power 1 by m. Okay, so that's simple, and I will again give you the ln property here. I'll write that down here because a ln of b can be written as ln of b to the power of a. So we just use this property to rearrange our terms once again. What's the next step now? So the next step, now if you follow hopefully where I'm going, so now you see ln of a minus ln of b. We can combine that equations as well, right? Ln of a minus b is nothing but ln of a over b. So then that gives us this value being equal to 2 into 10 to the power minus 7 times I. And if you combine these two, what you're going to get is this will come in the numerator now, because let me write this down here. Let me write the formula down here and then I'll explain what happened. So you're going to get ln of, so I'll change colors again, write this, so on all the way up to d1 of m, and all of this is raised to the power 1 over m, and then we divide this by d11, d12, so on all the way up to d1n, and this is to the power 1 over n, and this is because ln of a minus ln of b can be written as ln of a over b, which implies that if there's ln of 1 over a minus ln of 1 over b, that will be nothing but ln of b over a. Okay, so that's just the property we use and we get this formulation. And this is the equation for the flux linkages of conductor 1. So what you see here is for conductor 1, it's in the numerator, so it's very similar to all the formulas we've seen so far. It's 2 into 10 to the power minus 7 times I ln of, in the numerator you have all the distances from that conductor in that strand in conductor X to all the strands in conductor Y raised to the power 1 by m, m being all the strands in conductor Y, and down below in the denominator you have all the distances to the different strands within conductor X itself. So we can generalize that and say lambda of k is going to be 2 into 10 to the power minus 7 I ln of, we're going to use a new symbol for product, which is capital Pi. It's similar to sigma, and I'll explain that in a minute. M going from 1 prime to m, d of km to the power 1 by m, and this is going to be the numerator, and the denominator is going to be n going from 1 to n, d of dkn to the power 1 by n, and that is our formulation for the flux linkages for any conductor K. So here, let me just write a side note. So similar to, you have sigma for summation, and then you have pi for product. If you already don't know that, that's what pi, capital Pi stands for. So if I write delta dkm, m going from 1 prime to m, all that means is d1 1 prime, d1 2 prime, so on all the way up to d1m. That's all the product symbol is. All right, so that was for one strand. Now for the whole conductor, so we got the flux linkages for one strand K. For the whole conductor, lambda x, we'll have the summation of all the conductors, right? All the way up to n in this case, because x has n strands, which can also be written as k is equal to 1 to n lambda of k. But we're going to now, if you see 2 into 10 to the power minus 7 I is going to be common, and then you're going to have ln for lambda 1, for lambda 2, lambda 3, and we know summation of lns can be written as a product of ln itself. Okay, so if we expand this, then lambda x is going to be 2 into 10 to the power minus 7 times I times ln of, so for lambda 1 we have d1 1 1 prime, d1 2 prime, so on all the way up to d1m. I can write plus ln of lambda 2, all the fixtures for all the products for strand 2. So that's all the distances for strand 2. But instead of writing plus ln, I'm going to combine that and say that that's a product in itself, right? Ln that become ln a plus ln b, so I'll just combine that to ln a times b. So then that becomes 2 to 1 prime, distance from strand 2 to 2, so on all the way from strand 2 to m, and you're going to have all this all the way to your strand n, where the distance from strand n in conductor X to all the different strands in conductor Y. All of this and all of this is raised to the power 1 by m divided by, and the denominator is going to be again very similar, just the distances within conductor X itself. So we're going to have that, and this is going to be all the way to your conductor N, so on till conductor N raised to the power 1 by n. And this this can also be written as a general formula, where lambda x is going to be given as 2 into 10 to the power minus 7 times I, and then you're going to have ln of product of k going from 1 to n. In the numerator, you're going to have product of m going from 1 prime to m dk of m 1 by m, and in the numerator you're going to have n going from 1 to n dk of n 1 to the power n, and this whole thing's in a bracket. That term can be written as this generalized term, Weber turn per meter. I want you to give this a thought, expand this term, and you should get your lambda x as being equal to this. This is nothing but, if anyone's done programming before, there's a double for loop here. So you first do this loop and then you do this loop. So you go from start from k equal to 1 and then you substitute m. So you get k equal to 1, k stays steady, and then m changes from 1 prime all the way up to m, and then k becomes 2, and then you go again and repeat this cycle. You do that from the numerator and you do the same thing for the denominator. The one important thing to notice here is in the numerator, here you have m times n terms. So you have n times, so this is 1, 2, all the way up to, so this is 1 times m, 2 times n, so 2 times m, so on, going all the way to n times m. So you have m times n terms. That's a mouthful to say. And then you have here the same way, you have 1 to n, 2 to n, so on, all the way n to n. Therefore you have n square terms in the denominator. Similar to how we got lambda x, we can also get, similarly, we can get lambda y is going to be 2 into 10 to the power minus 7 times I ln of, you'll have your product function again, k going from 1 to m this time, and in your numerator you're going to have n equal to 1 to n. Remember, in this case it was distances from all the strands from x to y. In this case it's going to be from y to x in the numerator. So it's going to be dkn, and it's going to be 1 to the power n, and here it's going to be, remember this is capital sigma, m from 1 prime to m d of dkm raised to the power 1 is to m. I am hoping that's a lot for you to absorb, and that's why I'm going to stop right here, and that's why I'm not going to talk about inductance in this video. I'm going to make a separate video for that. I really want you to go over this once again, probably absorb all the math, understand the generalized terms. Once you understand the generalized terms, it's easier for you to expand in the future as well and understand them. If you have any questions, as always, please feel free to ask them. Leave your comments in the comment section below, and do subscribe to the channel so any videos that we post, you'll get a quick update on them. And I'm going to be posting the next video where I discuss the inductance of a single phase conductor very shortly. So till then, take care and have fun.